تخصصه أكتر في التوربulence، فهو هيدينا محاضرة عن ال vortex array model for unsteady wake of a periodically pitching airfoil. النهاردة الدكتور أحمد عنده over 50 published articles في peer reviewed journal غير ال publications وال patents في السنسور في ال innovative sensor اللي هي بتستخدم في ال measurements بتاعة ال wall pressure وال wall shear stress. يعني نخلي الأسئلة في الآخر، ندي الأول فرصة إن هو يعرض اللي عنده وبعدين هيكون وقت الأسئلة.
شكرا يا دكتورة آية. وأنا قبل ما ابتدي أحب أشكر الدكتورة آية والدكتور زكريا على الانفيتيشن، والدكتورة آية على مجهودها في إن هي تنظم الفيزيت يعني وإن هي تحققها يعني to make it happen. شكرا. التوبيك اللي أنا هتكلم عليه اللي هو الدكتورة آية قالته is over here. الشغل ده أنا عملته with my collaborator, with my colleague Manoj Kuchis-Fahani in our department, in the mechanical engineering department. The motivation for this work is recent interest in developing unmanned micro-air vehicles that are a few centimeters in size, and they can fly at low speeds of about 10 meters per second or so. Now, if you combine this characteristic length scale and characteristic velocity, then you can calculate a Reynolds number that is actually of the order of 10 to the 4 or smaller. Now, this Reynolds number is much smaller than the typical high Reynolds number flyers like airplanes that we use for transportation, etc., which typically are well beyond the 100,000 threshold. And the problem with this is that at these kind of low Reynolds numbers, you actually cannot really generate good enough lift anymore just using the traditional high Reynolds number airfoils, because the boundary layers at these low Reynolds numbers are laminar, and as a result you have a problem with laminar separation on these airfoils. And the high Reynolds number aerodynamics are based on thin attached boundary layers, whereas at low Reynolds numbers, the boundary layers, because of viscous effects are more important, are actually very thick. And this actually led people to start thinking, looking at nature, to start to develop effective flying methodology at these low Reynolds numbers. And of course, the natural thing is to look at birds and insects, etc., which do fly very effectively at this kind of low Reynolds numbers. Now, so this is the main motivating point, but once you actually have something that flies with flapping wings, then you get a number of other advantages. You can actually have high maneuverability, you can have vertical takeoff and landing, and you can also have wind gust tolerance. So in unsteady flows, birds can actually, within reasonable variations of the wind, birds can actually maintain their position. So all of these advantages then come along. Now, in fact, in recent years, you can actually go buy sort of toys actually that are built that are based on this flying wing principle. You can actually buy this for your cousin, kid or grandchild. And in addition, there are actually more serious ventures like this hummingbird nano flyer that was built by AeroVironment, actually with support from DARPA. And if you go on YouTube, you can actually see this thing flying. And in fact, when you look at it from far away, you cannot say that this is not a real bird. Now, of course, you can build things, but it's not uncommon that technology actually leads science. So even though we can actually build things, that doesn't mean that we understand the science in depth. And therefore, there has been, because of this motivation, there's been a lot of interest in studying the aerodynamics of these flapping wings, and the problem is actually very complex. So you're talking about massive three-dimensional separation. This separation, the separated shear layers roll up into these large-scale organized vortices that, in fact, dominate the unsteady forces on these wings. In addition, similar to birds, you might want to make these wings flexible because there are certain advantages. And if you make the wings flexible, then you start to go into a different kind of problem where you have to worry about flow structure interaction. So because of the complexity of this problem, then there are actually many unanswered basic science questions. And I'm only listing a few of these over here. For example, in these kind of flapping wings, you get different kinds of vortex structures from the leading edge of the wing, from the trailing edge of the wing. And if the wing, which in a practical application would be the case, is three-dimensional, then these may actually be connected through the tip vortex, and you can form things such as what's called arch vortices, and becomes highly complex. So there's a need to understand these different vortex structures and how they generate forces on the wing. Also, imagine you're designing one of these things, so you're going to choose a flapping wing. You will need to choose a frequency for flapping, you'll need to choose an amplitude, you'll need to choose a trajectory. If you want to generate thrust, I will show you in a few slides the basic physical mechanism, how you can actually generate thrust by moving a wing up and down. If you're going to move periodically up and down, should you do it sinusoidally? Should you follow a square wave? Something more complicated? So you need to understand how these different trajectories will affect the resulting forces on the wing. Similarly, what is the effect of frequency, amplitude, etc.? If you want to generate lift, you will probably end up doing some non-symmetric oscillation in order to generate a preference in the force in the upward or in the downward direction. If the wing is flexible, how does this alter things? So if you do all of these studies for rigid wings, what happens if you have flexibility? Would this give you an advantage that you want to capitalize on? If things are three-dimensional, short wings, which would be the case generally, how does this affect things? And finally, if you study these physics and others that I'm not listing here, and you understand them, eventually to benefit from this technologically, you want to use this physics to develop efficient design tools that you can actually use for designing these flapping wing flyers. The reason is that certainly you can do a fully resolved direct numerical simulation of this problem. It's too expensive in order to do any engineering design with it. So what you need is something that is very efficient, that can run very quickly, and you can change parameters and see what happens to the design. And the talk that I'm going over today, in fact, is a step in this direction with the focus on the thrust force that is developed on the wing. Now, because the problem is so difficult, you can certainly choose to go ahead and study an actual flapping wing flyer, or you can actually study a batten flight or some insect, etc., which people actually do. But the thing is, it becomes so complicated and it becomes so specific to this flyer or this particular insect that you cannot generalize the findings. So what you really need to do is to simplify the problem, study model problems that have the essential physics of the more complex applied problem. And once you understand it in its simplest form, then you start to build complexity towards the actually full complex problem. And what people have done in this kind of problem is the typical canonical or model problems that they use is they take a wing and they either move it up and down, which is known as pure plunging motion, or they oscillate it around some axis of rotation, which is pure pitching motion. And in many instances, actually, you combine the two. And in fact, that's actually the more efficient way of doing this kind of flapping motion. One thing I want you to note, because unfortunately, I don't have it anywhere in these slides, is the definition of the angle of attack is that if you connect the leading and trailing edge of the wing, then the angle between the free stream and this chord line is what I call alpha, or the angle of attack. Now, in this particular talk here, we actually are going to focus on pure pitch oscillation, where we have a NACA 0012 airfoil that is pitching around the quarter chord point. The frequency of oscillation is F. The axis system that we will use is at the trailing edge at the axis of symmetry. So it doesn't actually move up and down with the trailing edge. It's fixed in space as shown. This is X. This is Y, the vertical direction. And we're going to focus on small amplitude oscillation, and we'll oscillate the airfoil at frequencies, which in the world of aerodynamics, people like to think of it in terms of this non-dimensional or reduced frequency that I have over here, where the frequency is normalized by the chord and the free stream velocity. And we'll go to frequencies K up to a value of 10, which is very high in this kind of application. Now, if we actually look at the wake of this airfoil using some dye flow visualization, what you will see is that as the airfoil oscillates up and down, you actually form this highly organized periodic train of counter-rotating vortices. So you can see the one on top is in the counterclockwise direction, and the one on bottom here is in the clockwise direction, and then they basically repeat in an organized fashion. This particular flow visualization image gave us the idea of why not try to model the wake using a train of vortex or an array of vortex structures. And if this is an effective way to do it, then we can use this to actually calculate the velocity field behind the airfoil, and then apply the integral momentum equation to calculate the net force, streamwise force that's acting on the airfoil. Now, in the remainder of the talk, we will characterize this kind of vortex configuration using 3 parameters that I would like you to remember. And the white doesn't show up very well here. But if we take the 2 vortices with different sense of rotation, the spacing in the cross-flow direction or y direction between their center, we will call it D. The spacing in the streamwise direction between a vortex and another one with a similar sign, we call it A. The circulation of the vortex, which is an indication of the strength of the swirl that the vortex produces, is gamma. And plus will be in the counterclockwise direction, and negative will be in the clockwise direction. The specific objectives is that we basically this kind of an array of vortices model. We will the main objective is to try to assess how well will it work for both harmonic oscillation, purely sinusoidal, as well as non-harmonic oscillation, which I will do at the very end of the talk briefly. And in order to figure out if the model is doing well, we will compare data against laser Doppler velocimeter or LDV measurements that were done by my colleague back at Caltech in 1989. We will then employ this model to compute the net force acting on the airfoil and compare it against the data in the literature to actually see how well it can predict the force. And once we have confidence that we can model the wake accurately, then our objective will turn into using this model and varying the vortex wake parameters, the A, the B, and the gamma, and see how these parameters are related to the force acting on the airfoil. Now, a couple of slides briefly about the experiments. I've already described the configuration. The measurements are all done at one chord downstream of the airfoil over a domain that extends from half a chord below the airfoil to half a chord above the airfoil. Reynolds number is in the range 11 to 12,000. And we're looking at 3 different frequencies of oscillations. As I said, the amplitude is kept fixed, and the corresponding K values for the low, medium, and high frequencies are listed over here, and they range between 7 and 10. Now, if you look at the flow visualization associated with each of these oscillations, so this is done with dye. That entire experiment was done in water, and the dye is injected through the airfoil. What you can see are the flow visualization images here: low, medium, high frequency. To the right of each graph, there's the actual measurement. Remember, is done somewhere over here, one chord downstream of the airfoil. The airfoil is actually not captured in the image. It's somewhere over on the left. And that's actually the mean velocity. So this big U means it's an average velocity, and mu means it's in the streamwise direction. So this is the mean velocity profile measured in the wake 1 pore downstream for these 3 different conditions, normalized by the free stream velocity. What's actually missing in this slide, which I would like to describe first, is the picture of the velocity profile of an airfoil that is stationary, not oscillating. So imagine with me that you're starting with 0 frequency and then increasing the frequency down. In this case where you have 0 frequency, what you expect to see for the velocity profile is in fact something that is at the free stream velocity away from the airfoil, and then you develop a wake or a velocity deficit, and then you go back to the free stream. This momentum deficit in the wake is produced by the drag that's actually acting on the airfoil, which causes a deficit in the momentum flux downstream of the airfoil. And the vortex structures would also consist of pairs of counter-rotating vortices, but there's a very important difference. In that case, the positive vortex would be below the center line, and the negative vortex would be above the center line. And that is what is known as the classical von Karman vortex street that you would find in the wake of basically any bluff body or airfoils such as this one. Now what happens as you increase the oscillation frequency, you reach this interesting condition where the vortex structures, they are basically, as I said, they're going like this on top and like this on bottom. And then as you oscillate the airfoil, then they move. In the one on the bottom moves up and the one on the top moves down, and they align themselves to the center line. This is what's called the neutral condition. At this neutral condition, you can see the vortex center lines are aligned with the axis of symmetry of the airfoil. And what's special about this condition is if you actually measure downstream of the airfoil, the mean velocity profile gives you an indication that the airfoil doesn't even exist. It just looks like uniform free stream. If you continue and you actually oscillate it even further, then you get the positive vortex to move up and the negative vortex to move down. And what happens then, the top vortex induces velocity in the forward direction. The bottom vortex induces velocity in the forward direction. So, of course, this is unsteady flow, but in the net, you actually get a jet behind the airfoil instead of a wake. And you have the possibility of actually producing thrust. So this is the basic physical mechanism that actually results in the development of thrust by oscillating the airfoil. And the harder you oscillate it, in this case harder, quote unquote, meaning higher frequency, then in effect then you make this jet stronger and you make the thrust even stronger. So with this background, then our focus now is going to turn into modeling these vortices. And in order to do this, I will digress for a couple of slides to give some background. Our model will rely on describing the vorticity field. Vorticity, or omega over here, is a measure of the angular velocity or the spin rate of a fluid particle at a particular point in the flow. And you can calculate, if you know the velocity field, you can actually calculate the vorticity field out of it just by taking the curl of the velocity field. However, our model is, we will subscribe the vorticity and we want to calculate the velocity out of it. So we, in effect, we want to invert this equation. And the inversion of this equation is what we call the Biot-Savart law. Now, the Biot-Savart law is something that's actually quite straightforward to derive. If you start with this equation for the vorticity, and then you use with it this vector identity, which you can apply for any vector. Then, in this case, we apply it for vector u. And we capitalize on the fact that this is incompressible flow. And because this is incompressible flow, then the divergence of the velocity field is 0, and we can basically plot that del cross u equals omega from here, and we get this particular equation. So this particular equation, you can think of it as an equation in the unknown field u, given a known field omega, and this is a very well-known equation, which is Poisson's equation. The solution to Poisson's equation is known through Green's function, which is simply a volume integration of the right-hand side, which you can think of it as the forcing function, and multiplied by Green's function and integrated over the entire volume. You can do some algebra, and you can put this velocity calculation in terms of the vorticity in the famous form of this Biot-Savart integral. And the most important thing that I would like you to see from this integral, notwithstanding that it has vector form, etc., is that if somebody gives me the three-dimensional spatial distribution of vorticity everywhere, then I can calculate this integral and get the velocity field out of it. The one thing that I would like you to keep in mind is that the velocity field in this case is known within an arbitrary potential flow field that you can add on top of this. Because if you take the curl of what we calculate plus the curl of the potential field, the curl of the potential field is 0, and as a result you will get back the same vorticity distribution. So this is the key for our model, is the Biot-Savart equation. Now, so let's see what kind of vorticity distribution we're interested in. Remember, our flow visualization shows this train of vertical structures. So let's try to model one of these vortices. So if we say we have a vortex that's located in the two-dimensional plane, and we're not worried about z because the problem we're dealing with is two-dimensional, so everything is uniform into the screen. Then we say it's located at xc,yc and has strength or circulation gamma 0. Then this vortex induces some velocity at a distance r away from the center that has a streamwise or x component u and a cross-flow component v. In our model, what we decide to do is to actually say that the vorticity distribution for this vortex is given by this Gaussian format over here. Now, this is a choice that we make. There's nothing that forces us to make that choice. So, for example, somebody might choose a potential vortex, which is one that has infinite vorticity at the center, but actually has 0 core size, so the circulation is still finite. And in fact, in that case, you get back the classical von Karman model. And if you do that, however, as you know, that kind of vortex doesn't exist in reality. You don't have a vortex that has 0 size and infinite vorticity. Now and there are different kinds of vorticity distributions that you can use. You can use a solid body rotation type vorticity distribution, etc. Now, we chose to use this Gaussian distribution where the vorticity is maximum at the center and decays as you move out in the known bell shape, where in this case, this big R is a measure of the radius or the size of the actual core of the vortex. And if this is a good choice, our model will give us good predictions. If not, then we have to change things. Now, given this vorticity distribution, we can then plug it into the Biot-Savart distribution or law in order to get the corresponding velocity. And we can get the streamwise, the u and the v velocity using these expressions over here, where the gamma of the circulation is defined as such. Okay, now that we get this, we can now extend the model into an array of vortex structures as shown over here. And as you can see, this is consistent with the flow visualization that we saw, where we have the counter-rotating vortex pairs, the parameters A, B, gamma, the core radius. One choice we actually need to make is the length of this array. How many vortex pairs do we need to include in the model? Once we make that choice, then we end up with a capital N vortices, and the expression in the summation here is exactly the expression for u that we derived in the previous slide. And the same thing for v over here is the same expression as we derived for v in the previous slide. So if we sum the velocity produced by each vortex over all n vortices, which is related to the length Lx, then we can actually compute the resulting velocity field that is induced by the vortex array. And however, in addition, we add on top of this uniform flow u infinity because we need to meet the boundary condition that as you go far away, the velocity decreases to u infinity. And this is allowable because, as I said before, that the Biot-Savart calculation gives you the velocity field within an arbitrary potential flow field that you actually pick to match the boundary. So this is our model, and what we need to do then is to pick A, B, R, gamma, and Lx. Lx will basically increase it systematically until we have enough number of vortex pairs that there's no change in our solution anymore. So essentially it's a convergence parameter. A, B, gamma, and R, we will choose them to get the best agreement with the data that we have. Now, as far as Lx is concerned, what I show over here is a calculation just as an example for one of the cases for oscillation frequency of 6 Hertz. What you see over here is as I showed with the with the visualization, you expect this kind of jet profile in the wake of the airfoil. We're repeating the calculation of our model where Lx equals to 2 wavelengths, 4 wavelengths, 40, 320. This is the mean streamwise velocity. This is the fluctuating streamwise velocity, or URMS. That's the profile across the wake. And this is the fluctuating cross-stream velocity, again, profile across the wake. You can see when you look at all of these three plots, you can maybe barely see the red line. After this, all lines collapse on top of each other. So what this tells us, you just take 2 wavelengths, or more if you want, but 2 wavelengths is good enough, and then you have convergence. Okay, we take that and we find these parameters for the best matching with the experimental data. And what I show you right here is for the lowest frequency case. Remember, we have low, medium, and high frequencies. Each one of these plots that you're looking at is the calculated velocity profile for a particular phase of the vortex structure. Remember, this vortex structure, as time goes on, moves downstream. So we take different instants in time to cover a full oscillation cycle. So each one of these plots, you'll see there's a phi number up on top that indicates the fraction of the cycle for which the velocity profile is shown. This phi equals 0 is at the beginning of the cycle. Phi equals 0.5 is at halfway through the cycle. And beyond 0.5 to 1, actually you can figure out by symmetry. Now, in order to orient you in terms of the vortex structure for the location of the calculation, which is indicated with the red line over here, so we calculate the velocity over a vertical line. You can see that at phi equals 0, the positive vortex is located at the location where we're doing the calculation. At phi equals 0.5, the negative vortex actually is located at that position, and at 0, it's halfway in between. The graph here shows this bracketed U is the phase average velocity, which is the velocity at that particular phase of the cycle. The solid line is our model, and the red symbols are actually the experimental data. I should also mention that the LDD measurements actually contained only the streamwise velocity, a single component of velocity. So this is the only comparison we can make. As you can see, the comparison actually is quite good for all phases that are shown over here. Now, in addition to this, I will show you the full video of, so this is a computed, this is the computed so this is the computed velocity across the wake. You see here are the train of vortices going by, where in this case black is negative and red is positive. And notice how when a vortex coincides exactly with the position of the calculation, how we get the highest shear, which is induced by this vortex going by. Now, because in this case the vortices for this neutral condition are aligned on the center line, so whatever the positive vortex does is exactly cancelled by the negative vortex, so the net effect is just uniform velocity across the wave. And that's how we get the neutral condition. So remember, this is the key in the generation or in the switching from drag to thrust is the movement of these vortex structures in the wave. Now, we can also look at the full statistics here, the mean and RMS profiles for U, the streamwise velocity. Again, we get good agreement here. The same over here for the RMS. And the one advantage of the model is, in fact, if you have only single velocity measurements and you can reproduce the velocity with this good accuracy, you can, in fact, use this model to extract the cross-stream velocity component. So if you don't have full field or whole field measurements capability, you can in fact do individual single point measurements in this kind of problem, use a model like this if the flow is organized and dominated by vortex structure in order to extract the other missing velocity component. Similarly, we compare with the highest frequency case, which